Let's look at some examples of solving second-order linear constant coefficient homogeneous differential equations when the characteristic polynomial has roots which are not real. Well, let's look at this simple differential equation which we've talked about before by just kind of guessing roots. Let's see what our technique now tells us. What is the characteristic equation? It's just going to be r squared plus 1 equals 0. What are the roots? Well, the roots will be exactly I and minus I. In other words, we have r1 equals 0 plus I, and r2 is 0 minus I. This is our lambda is the 0, and our mu is 1. So we have lambda plus I mu and lambda minus I mu. From what we just developed in the last video lecture, we can tell you that our solutions as purely real functions are y1 equals e to the 0 t cosine of mu times t, which is t. That's just cosine t. And y2 is e to the 0 t sine of 1 times t. That's just sine t. So cosine t and sine t are two solutions. You can check again, even though I hope you checked in general that this is true, but the Wronskian of these two functions, cosine t and sine t, that's just equal to the first function, cosine t, times the derivative of the second function, which is again cosine t, minus the derivative of the first function, which is minus sine t, so that becomes plus sine t, times the second function, sine t, and this is cosine squared t plus sine squared t. This is identically 1, which of course is never 0. So these are a fundamental set of solutions. And our general solution, I'll write it in this form and I'll show you why here, will be y equals a times cosine t plus b times sine t. Here a and b are any real numbers. We kind of want to understand the behavior of these solutions. Well, here's a neat trick when you're dealing with trig functions like sine t and cosine t, and when you study wave functions a lot, you'll get used to this, and we're going to be studying these a lot more when we talk about solving problems, real-world problems involving forced vibrations, unforced and forced. We would like to be able to express this in a different way. I claim you can write a cosine t plus b sine t as what I'll call r cosine of t minus delta. In other words, you can express a linear combination of a sine wave and a cosine wave as just a single sine wave, or expressed as cosine here, but a single one whose amplitude, r, is just the square root of a squared plus b squared, and delta, which is just the phase shift, is given by tangent of delta equals b over a. So when you use those values for r and delta, you can express this as just a single shifted sine wave, and that means that if you want to graph the solutions, all possible solutions for arbitrary in a and b, you get an arbitrary positive number here for r, and it'll be just a shifted sine wave, so it doesn't have to start like a sine wave or start like a cosine wave. It might in general look something like this. And it can go back in time as well. That's not a very good. So this should go down as far as it goes up. Anyway, you get the picture. The general solution to this differential equation looks like sine waves, but they can be of arbitrary amplitude and start basically anywhere in that sine wave. Let's consider a different second order linear constant coefficient homogeneous differential equation, this time y double prime plus 2y prime plus 2y equals 0. And for this one, the characteristic equation is r squared plus 2r plus 2 equals 0, and the roots are r equals minus b, which is minus 2 plus or minus the square root of. Note in your head that b squared minus 4ac is negative 4. Since that discriminant is negative, we need to write I times the square root of 4. That's the absolute value of that discriminant, all over 2. And when you simplify this, this is negative 1 plus or minus, since the square root of 4 is 2, that cancels. We just get negative 1 plus or minus I. In other words, r1 is minus 1 plus I, r2 is minus 1 minus I. So that we have solutions y1, which is e to the minus t, that's the negative 1 times t, this is our lambda, equals minus 1, and here our mu is 1. We have e to the minus t cosine of mu times t, which is just cosine of t. And we have y2 equals e to the minus t sine t. And then our general solution, just as before, again, you could check very easily that the Wronskian is non-zero, and you should do that. The general solution is y equals a e to the minus t cosine t plus b e to the minus t sine t, which we can write as e to the minus t times a cosine t plus b sine t. And just as before, we could write this as e to the minus t times r cosine of t minus delta, where again here r squared, or r is equal to the square root of a squared plus b squared, and tangent of delta is b over a. Now what does this look like when we graph it? It looks just like the solution we found before, only the amplitude r isn't staying constant over time. You can think of this now as the amplitude. The amplitude starts when t equals 0 at r, but then this e to the minus t means amplitude is decreasing as t increases, but this cosine of t minus delta is just a wave function. So to give you a kind of impression here, now you're talking about a sine wave with decreasing amplitude, and it's hard to draw this. Let me erase it and try to draw this a little better. We could use straight axes to make a decent drawing in this case. Let's see. Very quickly, because of the exponential e to the minus t, the amplitude just dies down and tends to 0. And all solutions will look like this. You'll just get different phase shifts and different values for r, different amplitudes, but all solutions to this differential equation will die down like that, starting from t equals 0. This is our t-axis here, and this is our y-axis here. Finally, let's look at a very similar differential equation. The only difference between this and the previous one is we have a minus here, so the characteristic equation is r squared minus 2r plus 2 equals 0. The roots are minus b, which is now 2, plus or minus the square root of, again, b squared minus 4ac is negative 4, so we'll have I times square root of 4 all over 2, and that's just equal to 1 plus or minus I. So here our lambda is 1, and our mu is 1. So our general solution, or our two solutions that we find are y1 is e to the t cosine t, and y2 is e to the t sine t, so that the general solution, again, check that the Wronskian of these two is non-zero, so that this is a fundamental set of solutions. The general solution is y equals e to the t times a cosine t plus b sine t. This is just a times y1 plus b times y2, which again I'll write as y equals e to the t times r times cosine of t minus delta, where the r and the delta are just as before. And the way the solutions look is a little different from before. The amplitudes, instead of dying down with an e to the minus t, will start to blow up. So you'll get a phase-shifted sine wave, which starts with some sort of amplitude, but then the amplitudes are going to get bigger and bigger and bigger forever. And they'll get bigger and bigger and bigger very rapidly. You get the picture. The amplitudes, if we graph this, would be an exponential function of increasing amplitudes.